Welcome. This is Dawn Atanasio at George Washington University Law School. And it's my great pleasure in this segment of our program to welcome Dr. Jennifer Shafer. She's going to be speaking today on reprocessing technologies of tomorrow, fixing economics and improving non-proliferation. Dr. Shafer is the program director at ARPA-E and a professor at the Colorado School of Mines. We are running a bit behind, so I'm going to refer you, well, in any case, I would still refer you to her biography to understand all of her other accomplishments. And at this, I will turn it over to you, Dr. Shafer.
All right. Well, thank you, everybody, so much for being here today. And I'd really like to thank Donna for the invitation to come and present on the topic of reprocessing and what we're starting to do and think differently about in this space. So hoping that everybody can see my slides here, and I'm going to go ahead and move forward with the presentation as soon as I can. There we go, share screen. So I'm Jennifer Shafer. I'm a program director at ARPA-E. My background originally is in chemistry related to reprocessing. I'm also a professor at the Colorado School of Mines, and I've been working in this project area. And Robert Ledoux is also a program director at ARPA-E, and we've been looking seriously at the back end of the nuclear fuel cycle and basically what things that we can be doing with respect to this. The talk that I'll be giving today is looking at reprocessing technologies of tomorrow and fixing economics and improving nonproliferation. So a little bit about ARPA-E and nuclear fission. So one of the things about the agency, for those who don't know about ARPA-E, is it's an incredibly ad hoc agency on some level. We have items within our statute that we work explicitly towards, broadly speaking, things like reducing emissions, increasing energy efficiency, et cetera. But one item that was added explicitly to our mandate in 2020 was being able to improve the management, cleanup, and disposal of radioactive waste and spent nuclear fuel. And that's actually what we have shown here. And so when we actually consider the broader nuclear reactor fleet, so both the current fleet as well as the advanced reactor fleet, we can talk to some of the program space that's considered both the management of used nuclear fuel and nuclear waste, but also what technologies and programs that ARPA-E has invested in to date that intersect with the deployment of advanced reactors. So there's a couple of different factors in this space to consider. Just for folks' awareness, there were 2 programs launched looking at advanced reactor deployment, particularly targeting decreasing the advanced reactor CapEx and OpEx of advanced reactors. And the CapEx target program was Meitner, and then the OpEx program was Gemini. And so those are 2 programs that are in the portfolio right now. Gemini is looking a lot at digital technology and in particular digital twin technologies with respect to this. And that's actually a portfolio that I'm also currently managing. When we look at Onwards, so this is a program that Bob Ledoux just actually produced and is working through. This is a program that was dedicated to decreasing the disposal impact of materials arising and used nuclear fuel arising from our advanced reactor fleet. And so that's a program that ARPA-E has just launched and moved towards. And CURIE is actually the program that I've been leading, and this is looking at taking our current used nuclear fuel and actually deploying this as fuel for our advanced reactor fleet using reprocessing technologies. And so I'll be speaking about why this is an important time to be considering this and why there are options on the table from a technological perspective that things that could be significantly enabling in this space. So at the core, when it comes to CURIE, there's 2 things that we are really looking at addressing specifically, though we also have broader technical metrics that hit at this. So one of them is that can reprocessing be done affordably with respect to the current market? So basically, can we provide fuel and technologies that can be used for advanced reactors that are competitive? And then also, can safety and safeguards be maintained or improved when reprocessing, basically relative to the once through cycle? So can we actually develop a reprocessing scenario that has safeguards and materials accountancy aspects that are actually preferential to what we're currently doing now? So why is reprocessing actually such a compelling technology, at least in the eyes of this program director as well as the agency? So one is it provides a unique opportunity to stabilize our fuel supply. And so Bob was able to talk about significantly the role of supply chains and the aspects that need to be paid attention to with respect to supply chains broadly with respect to the nuclear fuel sector, but it actually turns out that the HALEU fuel supply and just fuel supply in general is crucial to manage with respect to the advanced reactor fleet, especially considering current world events. And so this is potentially one mechanism that we could stabilize as well as improve the domestic security of. We can also anticipate that there is a potential social benefit associated with reprocessing technologies from the standpoint that you have more flexibility in how and where you deploy a reprocessing facility with respect to the broader community, as opposed to other options which perhaps maybe you don't have as much freedom, where you might go to mine uranium because the uranium deposits are only in a particular place. Right, so this provides an aspect of flexibility, which could also confer social benefit as well as environmental benefit that we are attentive to. This provides improved resource utilization. For example, the 86,000 metric tons of used nuclear fuel that we currently have, depending on the type of reactor that you deploy, you can imagine providing fuel for fundamentally about the next 50 years or longer than that, based on what we already have stock in hand. It also potentially enable fuel takeback. This is something that's been attractive to some countries as they've been looking to bring in advanced reactor technologies from other countries, the possibility that maybe countries selling to them would be willing to take back their fuel. And if we're in a position where we can actually reprocess the fuel, then this would be enabling because it would render a much decreased waste and volume footprint. And of course, this provides an opportunity for the U.S. to assume U.S. leadership with respect to this if we fundamentally reimagine our approach to reprocessing and basically set a new standard for how this is to be done. There are a couple of challenges, just a couple, with respect to looking at this. So one of them, of course, are economic factors that intersect with reprocessing. So we know the technology as it currently sits right now is at least about 6 times as costly as our current alternative technologies. So things like basically fresh fuel and HALEU enrichment and things of that nature. So another factor that we have to be very attentive to is nonproliferation and materials accountancy. And from a U.S. leadership perspective, we have to be very attentive to whatever treaty obligations we have, and just in general, what role we participate with in the world stage and how we are bringing technologies forward for us to have a strong position there. So as already said, we know that our technologies, current reprocessing technologies, cost on the order of 3 to 9 times that of fresh fuel, depending on which technology you're considering thinking about. Another thing when it comes to nonproliferation is that in general, there can be a concern with respect to the accumulation of separated plutonium and separated as well as accumulated material. And so I think that there are things that we can do in the development of technology to be attentive to this, to minimize the accumulation of material, as well as having a really robust and precise assessment of the material on hand. And so these are things that we are attentive to. And ultimately, what we would like to develop and build is a secure and affordable technology. So in considering the evolving landscape, what has changed? Why all of a sudden can we look at this and say, hey, we think that we have some solutions on the table that actually didn't exist when we were considering this, say, seriously, nearly 50 years ago as a commercial enterprise. So we know that climate change is something that is real and is causing us to have conversations and buy-in, frankly, for nuclear that we haven't seen in a while. So that's something that's important to keep in mind. We also know that advanced reactors and the types of materials that they use, they're going to have fuel needs. And it seems that this is a unique opportunity to both, whether we are taking our current nuclear fuel that we already have that's sitting on site at various reactors across the country, or we are taking fuel from our advanced reactor fleet, as Bob is looking at with Onwards, right? There's opportunities to intersect with the evolving advanced reactor landscape and how we might support that supply chain. We also know significantly more about the chemistry that could be deployed and used for these sorts of technologies. So this cannot be underscored enough that in the original Purex type technologies that were developed, right, we had only known that plutonium was an element for, basically less than 10 years, right? And so this has provided an opportunity or a springboard for us to think about how we might control the chemistry and how it's evolved, not only for plutonium, but the rest of the transuranics over the course of the next 70 years that frankly we've been studying these elements, as well as the importance of minimizing waste streams, not only just because that's good practice, but also because it adds significantly to the cost of your reprocessing facility. So these are all things that intersect with the chemistry, and how we execute and capitalize on that is of utmost importance. We know that we're also becoming much more effective with respect to the deployment and development of modular technologies as a country, and this is actually a nice opportunity for us to capitalize on the fact that we know that the advanced reactor landscape is uncertain right now with respect to the type and number of reactors that are going to be built. And so at this stage, you could make the argument that, the classical approaches that we've considered where one might deploy, 1,000 or a 3,000 metric ton facility that's processing that much fuel per year maybe isn't the right fit for basically the tenuous and kind of deployment schedule that advanced reactors are on right now. And so if we could actually take a more modular approach and basically build technologies and build facilities in a way that's compatible with the deployment timeline of advanced reactors, that would be enabling, both with respect to it keeps your economics consistent with industry, but then also it could minimize your actual accumulation of material that is not preferred. Digitization is something that's certainly come online, and this is something that is just starting to meet an intersection with advanced reactor technologies, but it can also have a transformative impact with respect to reprocessing technologies and how we monitor these facilities, not only for the benefit of being able to have accurate and timely materials accountancy, but also from the perspective of this is actually completely synergistic with operation and maintenance activities. And so we could potentially be entering a paradigm or potentially shifting the paradigm where up until this state, improving the safeguards of a facility is generally added additional cost. If the technologies that we're using are actually used to improve the materials accountants capability as well as improving the operation and maintenance schedule, then we're in a new situation where actually adding safeguards could actually have a cost benefit to the facility. And of course, we're looking at things like the possibility that we actually have a lot of aged fuel, so fuel that's sat around for more than 30 years. And that has ramifications as far as the types and amounts of off gases that occur when one goes to dissolve that fuel, and actually has ramifications for the type of facility that you might need to handle it, because you may not need so much shielding, you might not need the same off-gas capture capabilities because frankly you aren't dealing with the same radiation and hazard levels. All of this ultimately lends itself to an opportunity for us to be thinking about this seriously and really capitalize on the confluence of the factors that I've outlined here. Another thing that's absolutely critical in thinking about this is we've never actually taken a ground-up approach that considers all of these factors and the evolving chemistry and meeting advanced reactor designs and minimizing waste with the types of reprocessing technologies that have been developed to date. The types of technologies that have been used are actually co-opted from the defense program, and so as a consequence of that, they didn't have the same waste management attention nor economic attention placed, nor actually materials accountancy attention placed on them in the same way. Especially since things were so early stage. And so this is an opportunity, we think, to leverage things in an interesting way. So what do we need to do actually looking at a potential pathway to deployment of technologies? So we know that if we are here basically in 2021, and actually you can see that the slide's old, it was actually be 2022, we need to basically identify the technologies that we think are most compelling and most enabling in this regard. By 2025, perhaps complete a pilot facility design for something that could actually go through a regulatory approval and be discussed seriously. Hopefully we could get some regulatory approvals in place, and then perhaps we could actually have a pilot facility operational around this timeline. So well, you can see that I'm not explicitly proposing a solution that's going to get us there tomorrow as far as reprocessing technologies, but we actually think that this is something that could be broadly enabling even on the timelines considered here. So I'd just like to say a couple of things about the Onwards program and CURIE program as we understand them. So as I mentioned earlier, I'm not the program director responsible for Onwards. This is Bob Ledoux. And what Onwards was really positioned to manage, and I'll go ahead and move myself here, is to develop technologies that could significantly minimize the disposal impact of waste from advanced reactors while maintaining disposal costs in the range of $1 per megawatt hour. Of course, the driver for that staying consistent within the current nuclear regulatory fund, or I should say nuclear waste management fund that was collected for management of used nuclear fuel, and basically staying consistent with precedent there. We know that basically this is how an advanced reactor closed fuel cycle could actually look. And Onwards is basically seeking to support the development of technologies that enable a 10x reduction in waste volumes or repository footprint with no weakening of safeguard standards. There is also an importance for better than 1% accountancy and fissile measurements, and we want to make sure that these can be executed in high radiation backgrounds, because actually the way that certain fuel cycle designs for for fast reactors and advanced reactors actually leverage the fact that you have short turnaround fuel associated with them. We'd also like to improve the proliferation resistance of uranium and transuranium materials recycling, as well as just, no pure fissile material streams produced during the processing. So we also want to make sure that we are not sending actinides to waste streams. A really important part for Onwards is also making sure that there are high performance waste forms for advanced reactors across multiple disposal environments. So this was something that we noticed when we looked across the fleet that had yet to be developed. Absolutely critical to the philosophy of Onwards is that the production of new waste streams is required to be minimal relative to a once-through fuel cycle and have an established path to robust waste form or final disposition. And so basically, we don't need to be developing any new waste streams that impact significantly the back end. So making sure that we're attentive to that up front, because really at the end of the day, that can not only serve as a significant cost liability, but also a regulatory liability, and social one for that matter. So when it comes to CURIE, so as mentioned earlier, this is the project or the program that I'm running. And so here we're looking at converting UNF radioisotopes into energy. So really we're looking to enable the economically viable reprocessing of used nuclear fuel from our current light water reactor fleet by resolving some key gaps and barriers that we've identified in reprocessing technologies, process monitoring, and facility design. And so when it comes to the global metrics here, of which we have several, we also are attentive to the waste volume and making sure that that is not ballooning. We actually want it to decrease significantly. We want to be able to maintain our disposal costs consistent within the bounds of the current nuclear waste management fund, or I should say the historical nuclear waste management fund. We also have a goal, and this is our cost goal, of providing a cent per kilowatt hour fuel cost for basically a 200 metric ton heavy metal per year facility. And so this is basically consistent with what we anticipate to be the market cost or hopeful market cost for HALEU when it is available to the market. And we also want this, and this is especially a kind of a double challenge, trying to do this on a small scale facility. So something, and I realize that 200 metric tons is still a lot of material, but this is smaller, much smaller than some previously considered facilities. So we also are very attentive to, and this is significantly different from Onwards, because Onwards was trying to just find safeguards and monitoring solutions for things that didn't even have a solution in place yet. For CURIE, we do have some established practices when it comes to materials accountancy and monitoring, or I should say really materials accountancy and safeguards. But what we're actually hoping to provide is in situ special nuclear material process monitoring approaches that are actually predictive and allow you to know within 1% uncertainty under the appropriate conditions what the post-process materials accountancy will be. We think that this is significantly enabling because currently when materials are processed at a given facility or accountancy maybe occurs on a monthly basis. And this is just a different dialogue that you're able to have if you're able to tell in real time that there's been a diversion from the facility. And then also we want the development of used nuclear fuel separations, which do not produce pure plutonium streams consistent with onwards. So what technologies broadly are actually enabling in looking at this? So as we already talked about the potential benefits, though some could argue limitations, especially if you're going after valuable short-lived radioisotopes of considering used old nuclear fuel, so greater than 30 years old. There's broader enabling tech that's considering here. These are things like additive manufacturing, AI/ML, things of that nature. Sensors and new sensors are also crucially important to this. We also talked about chemistry as well as some of the benefits of modular design. So one thing that I'd like to underscore with respect to digital twin opportunities is this is something that's already ongoing with the agency with respect to advanced reactors. And as I mentioned earlier, I'm currently managing the Gemini portfolio. And why we think that this is so crucial is that we can see through the use of digital twins and active monitoring that you can actually reduce your preventative maintenance work hours by things like 37%. If they're deployed, you can actually cut well-designed times in other industries by something like 80% if you're doing actually effective modeling. So this is something that we'd really like to bring to bear in the nuclear sector. And so as I mentioned earlier, the Gemini program is already looking at this for advanced reactors, and this is something that we hope to consider more seriously and actually are starting to consider in the Onwards program with respect to reprocessing technologies. The core tenet of Gemini was basically that we would like for the operation and maintenance costs of advanced nuclear reactors to be consistent with current combined cycle plants, natural gas plants, and basically driving that down significantly. When it comes to the chemistry, I don't want to spend too much on this slide, if only because I might be the only chemist in the room looking at this. What I'd like to suggest, though, is that there are actually some core opportunities to think about with respect to chemistry. One of them being that we actually have the ability to control the transuranics and their chemistry in basically a different way than we actually had available to us previously. And as a consequence of this, we know that we can actually much more effectively than previously bring all of our fuel cycle relevant transuranics, so things like uranium through americium up into this hexavalent state, or I should say this oxidation state, where they, at least in certain media, will obtain a similar chemical configuration. And this allows us to basically extract them in a combined way, which is enabling if you're trying to prevent pure plutonium streams from being developed. We also know, and there's some unique opportunities potentially in bio-based separations, not only because of, on some level, they're more neutral chemistry, which, frankly, sometimes every time you see an additional hazard associated with a chemical process, you can almost on some level think of it in terms of dollar signs, because not only of the additional engineered safety that one needs to provide, but frankly, you want people to be deliberate in working with more hazardous things, and that just requires additional time to make sure that everything is administratively in place. And so, this is compelling because bio-based separations would have that, would be intrinsically safer on a lot of levels than currently deployed things. But also you can actually have you could imagine developing certain separations where you maybe would actually only allow the separation to occur if there was a mixture of uranium and plutonium present, basically intrinsically within the molecule. And so basically, if you have pure plutonium, the separation doesn't happen and it's blocked at a first foundation chemical level. If you have a mixture of things, then it's actually enabled to be passed through. And that's based on basically the idea that certain proteins might maintain different configurations based on the metals that are actually present in them. So we can talk a little bit about sensors online monitoring. So basically, we know that offline technologies have increased cost, time, personnel, as well as decreased accuracy. We know that online technologies would allow more complex chemistries. So actually some of the things that I was talking about earlier, because you can really monitor it in situ and your chemical separation is not a black box, as well as in situ plutonium monitoring. And so we think some of the opportunities here are, potentially redesigning of your chemistry or your system to enable AI machine learning approaches, but also complex solution monitoring. And then basically, as we come to the fold here, when it comes to modular design and construction, I think especially at this time, though maybe someday we'll deploy a lot of nuclear, but building 1,000 to 3,000 metric ton of heavy metal per year facility within the US does not make sense at this time. We also know that the nuclear industry has struggled with dynamics and factors related to poor project management. We know that the CapEx is inaccessible. We also have the factors of unclear reactor deployment. We also need to develop a broader base of domestic expertise. And then as well, if you start smaller, this enables you to use perhaps more nascent stage technologies that are perhaps more underdeveloped at this time, but could scale more appropriately with a modular approach. Regarding safeguards considerations, you could imagine, there is this aspect of now you're considering looking at needing to safeguard or to perform complete material accounts on multiple facilities versus one facility. So this is something that you need to be thinking about as far as how you enable that monitoring. This is something where a digital twin and systematic facility design could be critical. Small facilities could be easier to safeguard or develop safety for, and so that's another plus. And then again, it kind of comes back to this idea of perhaps putting yourself in a position where you're more able to meet market demand at a particular moment, as opposed to perhaps oversupplying material that might come along with a larger facility. So that was in general the conversation that I wanted to have with you today. At the core of it, we think that this is a great time to be thinking about reprocessing technologies, what they could look like for the future, and how they might intersect with advanced reactor technologies. And I appreciate the attention that you paid. I can actually be reached here at jennifer.shafer@hq.doe.gov.